In this problem, I'm going to talk about the use of the force model with a two-body system. In this example, I'm of an incline with a mass on the incline. There's going to be a pulley at the top of the incline with a hanging mass. So we have a mass here, call that little m, with a string over a pulley right here, and I'll call this capital M, and this is theta. And we have a coefficient of friction here. It's a rough surface. So I'll call it mu k between the block and the incline. And if this is initially moving, let's say clockwise, the mass is moving down, we want to find the acceleration of the system. So this is important because it tells us that the frictional force is going to point down here in a minute. So we want to find the acceleration of the system. So we have two bodies, so we need two free body diagrams. So the first diagram is going to be with the object from the incline, and the second one is going to be the hanging mass, capital M. So for the object from the incline, we have an f of n. Draw that perpendicular to the bottom of the object. We have a tension here, T. We have an mg that points straight down, little mg, the weight, and then the frictional force, Fk. So those are the forces acting on the objects on the incline. The hanging mass, we have the tension pointing up, capital T, and then big mg, capital Mg, the weight of the object, capital Mg. Okay, so as we've seen before, because it's an incline, we're going to tilt the axis so that positive. Now, since it's moving upwards, I'm going to put the positive x-axis being up because that's the direction of the motion. And then Fy, I'm going to point that like that. Okay, so in our x direction, I have T, and if we break this up, we have a minus mg sine theta from our mg, and then minus a frictional force kinetic. And we will have an acceleration, so I'll leave it as that. In the y direction, I'm going to have an f of n minus an mg cosine theta, and there will be no acceleration in the y direction, so it won't go up and down like this. For the other mass, I'm just going to use standard xy axis here like this. So there are no forces in the x direction, and just for clarity, this should be capital M because it's the other object, capital M, no acceleration. And for the vertical forces, we have T minus capital Mg equals capital Ma, and there will be an acceleration. And the thing to note is that this is moving downwards, so we need a negative sign right here. Okay, so those are the force equations here, and the question is solve for the acceleration. So we're trying to solve basically for this acceleration here. Now note, the acceleration in the x direction for this guy is basically this acceleration. So these are one and the same. These are the same acceleration rates because the x acceleration, or this acceleration, is equal to that acceleration, assuming there's no stretch in the string which would affect that. But we're trying to solve for that. So my equations become, if I go up here, T minus mg sine theta minus frictional force kinetic equals ma, and then I also have T minus capital Mg equals capital Ma. So there's the acceleration rate. I took out the subscripts because they're the same acceleration. So what I'm basically going to do is I'm going to solve for T in this equation and plug it back up there. So T is equal to capital Mg, there's a minus sign here, from that minus sign right there, minus Ma. So I'm now going to take this and substitute it in right there. So this is step 1 if you want to call it, step 2 if you want to call it, step 3. So for tension, we have mg minus ma, that's the tension right here, minus little mg sine theta, minus, now f of k is mu k f of n equals little ma, And then Fn is what? Fn is mg cosine theta. So we have to do another step here. This becomes mg minus ma minus mg sine theta minus mu k mg cosine theta equals ma. So if I'm trying to solve for ma, I have a term here, it looks like, and I have a term right here. So I'm going to bring this term to the other side and factor out the a. So my step here becomes, if I bring this term to the other side, it becomes positive. So I have mg minus little mg sine theta minus mu k mg cosine theta equals ma plus capital Ma plus little ma. So you can say I can factor out the a. So the final answer is, if I write it right here, a is equal to mg minus mg sine theta minus mu k mg cosine theta, all divided by little m plus big M. So that's my acceleration rate. So if you look at this just from a equals F over m point of view, you have basically this force, mg pulling down, mg sine theta, and the friction pointing the other way, divided by the entire mass. So this is the net force divided by the net mass. One force pulling this way, that would be this in the upward direction, which comes downward here. Two forces pointing down, the frictional force and the mg sine theta, divided by m plus m, total mass. So it kind of looks just like this equation here. So that's the procedure you follow for a two-body system. Now, if the system were moving the other direction, let's say we're moving this way, then what would be happening? The frictional force will point upwards in this direction here, and this would be moving up, which would mean a plus sign there. But other than that, everything would be the same. So that's a demonstration of the use of the force model of the two-body system.